full energy levels are really low energy. Once you get to very low energy, you tend to stay there. We talked about a bowling ball not staying on the shelf forever. It's going to end up on the ground eventually. But if you dig a hole and throw the bowling ball down in the hole, is it going to suddenly come back up? No, you're going to have to put a lot of energy in to get it back up, right? Low energy is stable. So, what kind of elements have full energy levels? Noble gases. S2P6. Then we start the next energy level. Right after P6, we start another energy level, right? So, what atoms are going to do, they are going to arrange their electrons, change their electrons in a way that they end up looking like a noble gas. They're going to do what it takes to achieve noble gas configuration. This is going to be our answer why for just about every time we try to put chemicals together. They're going to do it in a way that gives them noble gas electron configuration. Everybody wants to look like the king. Everybody wants to look like the noble gases. Okay? But this is going to be a really important idea. You know, in the past I told you, these ideas just keep coming back. This is one that just keeps coming back. Okay? Second ionization energy. For elements that reach a filled or half-filled orbital by removing 2 electrons. The second ionization energy is lower than expected. It's easy to make things that are full or half full. So look what it looks like after you've lost 1 electron and see what happens when you take the second one. Is it going to end up full or half full? So, which elements are going to have low second ionization energies? Well, the ones that look full after they've lost 2 electrons. And full looks like noble gases, right? So they must have 2 more than the noble gases. So it would be the alkaline earth metals, the S2 group. Because if this loses 1 magnesium looks 1 electron, looks like sodium. When it loses the second one, it looks like neon. So alkaline earth metals always form 2+ ions. That's how they react. They react by making 2+ ions. Okay. What about third ionization energy? Which ones are going to lose that third electron easily? Well, the ones with 3 more than a noble gas, right? So that's 1, 2, 3. The ones in S2P1, the one in the boron family. By boron, by losing 3 electrons, it looks like helium. But when we say low third ionization energies, It means compared to other third ionization energies. Not compared to first, not compared to second, compared to other third ionization energies. Because that third ionization energy is going to be higher than the first. So when we say aluminum has a low third ionization energy, its third ionization energy is still higher than its second, but it's just low compared to other third ionization energies. And the fourth, well, the ones with the fourth ionization energy be low would be things in the carbon family. Yeah. But this should help explain these numbers. Remember, we got that big jump. The highest first ionization energy is helium. It's the biggest one on this list, right? Okay. That's the highest first ionization energy. But notice it's not the highest second ionization energy. Lithium has the highest second ionization energy. Why? Well, because lithium, after it loses one, looks like helium. I've lost an energy level. So I'm taking that new electron out of a lower energy level. And it's already positive. It's going to be a big jump. So I really should be comparing this electron, the second one here, with the first one. These two are talking about the same electron. They look like helium. Okay. Highest third is aluminum. Or sorry, beryllium. Yeah, beryllium. Because when you take two off, it looks like helium. So when you go get the third one, it's coming from a different energy level. The easiest one to take the third one off of is boron. Okay? Because by taking it off, you're making it look like a noble gas. Right? Because take the third one off, 1, 2, 3, the third one comes off, you're down to 2, you look like helium. But with a 5+ charge. Okay? So these jumps are about energy level difference. That this one is taking it from the first energy level, and this one's taking it from the second energy level. That every one of those jumps is an energy level difference. First energy level, second energy level. First energy level, second energy level. And it's easy to remove once you have a shield. Okay. Valence electrons. We talked about them briefly last chapter. Now we can talk about them a little bit more specifically. Electrons in the outer energy level are the valence electrons. They're the ones responsible for most of the chemical properties. And they're called valence electrons. So those in the outer energy level are valence electrons. And the outer energy level is just going to be S's and P's, because the biggest number always goes next to an S or a P. And the ones that aren't valence electrons, they're the core electrons. This is the basis for our shorthand. The core looks like neon. The valence electrons look like 3s1. The core looks like xenon. The outside looks like 6s2, 4f14, 5d3. So that's the basis for our shorthand. We didn't need to be specific about what the core was, because all that did was get in the way. But we need to be specific about the electrons on the outside, because those are the ones that are going to interact. So atoms in the same column have the same properties because they have the same outer electron configuration, right? We've said all this before. This is not new stuff. Same columns, same properties because of same electron configuration. Now we can add the idea of valence electrons. If they got the same outer electron configuration, they're going to have the same number of valence electrons. So last test, I asked you how many electrons were in the outer energy level of whatever atom it was. Okay. Remember that? I was really asking you for how many valence electrons are there. So you can write out the electron configuration and then find the biggest number and then count the number of electrons there. So if you had something like argon, 4s2, 3d10, 4p2. The biggest number is a 4, and there are 4 electrons. So this would have 4 valence electrons. That's one way to get it. That's the large and that's the long and complicated way. The easy way? Look at the group number. I picked 4p2, so I was talking about germanium, right? It's in group 4a. It's got 4 valence electrons. Oxygen's going to end in S2p4. It's going to have 6 electrons. It's in group 6a. That's why we like the ones with the A's. We use those ones with the A's, it'll tell us how many valence electrons there are. We should be able to figure it out anyway from the S's and the P's, but it's a lot faster just look at a number at the top. Okay. So the alkaline earth metals, how many valence electrons do the alkaline earth metals have? Well, alkaline earth metals is group 2a, so that would be 2. Group 2a has 2 valence electrons. Group 3a has 3 valence electrons. 4a has 4. 5a has 5. 1a has 1. And that gets us halfway through the trends for our 4 trends, because we've done atomic size and ionization energy now. Well, the next one was closely related, was ionic size. And ionic size, we first have to figure out what an ion is. We talked about ionization as removing an electron, and that removing an electron gave you a positive charge. So, the name for something with a positive charge is a cation. Try to make it easy to remember this. I used to say things like, I just can't think of anything positive to say about cats. No? No. How about this? Okay, I hate doing it, but it works so well that I do it every year. Here's how you remember. Cations are positive. Okay, I hate doing it, but it's going to work, isn't it? Cations are positive. Okay. And they form by losing their valence electrons. Why would an atom lose its valence electrons? to achieve noble gas electron configuration. Because if you take off the valence electrons, you are at noble gas electron configuration. Right? So, cations are going to be smaller than the atom they come from. Actually, I should put the word much. Say, whoa, 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 why much smaller? Well, we went into a big explanation that neon was smaller than lithium, right? Because it had a more positive nucleus pulling that second energy level in. And sodium was bigger than lithium because it had an extra energy level. But if sodium loses its electron, it now looks like neon. It's lost an energy level. But not only is it going to look like neon, it's going to have one more positive charge than neon does. So it's going to look like neon, only be smaller than neon. So sodium started off bigger than lithium, which was bigger than neon. Take one electron off, and it's smaller than neon. Because it's taking those 10 electrons and holding it in with 11 positives instead of 10. So cations are much smaller. There's a big drop for cations. And now I can finally talk about what the real difference between metals, nonmetals, and metalloids is. Metals form cations. Metals react by losing their electrons. That's what makes them metals. Metals are losers. They lose their electrons. And again, cations of the representative elements are going to have noble gas electron configuration. So it's going to lose enough electrons so it looks like a noble gas. Because once it looks like a noble gas, it's stable, it's low energy, and it stays there. Okay, next slide is about things we haven't talked about before. We've talked about losing electrons. We've talked about positive ions. But there are negative ions too. They're called anions. Not anions, not like onion. And it's not cation. And it's not caution because there's a U missing. It's cation and anion. A negative ion. A negative ion. Okay, so how are you going to make an anion? Are you going to lose protons? Got to gain electrons. How many will it gain? It'll gain enough to look like a noble gas. I told you that driving force was the reason. Everybody wants to look like a noble gas. So they're going to gain enough electrons to look like a noble gas, and they're going to fill up their outer energy level. If it's not already full, they're going to fill it up. So chlorine is in the third energy level. It's going to gain one electron to look like argon. What's that going to do to the size? So I did have 17 protons holding in 17 electrons. I gain an electron, now I got those 17 protons trying to hold in 18 electrons. Are they going to do as good a job at holding 18 as 17? No, so anions are a little bit bigger than the atom they come from. Not a lot, a little bit. because they're filling up the energy level they're already on. The cations are losing a whole energy level. And that's going to make a big difference. So, metals form cations. What do you think the next line is going to be? Non-metals make anions. That's the difference. The difference is metals are losers, non-metals are gainers, and metalloids sometimes lose, sometimes gain, depending on what you put them with. You put a metalloid with a loser, it's going to pick up those electrons. You put the metalloid with a gainer, it's going to lose electrons. That's the real difference between metal, non-metal, and metalloid. That's how it can have the properties of both. That's what the properties of both was. Sometimes it loses, sometimes it gains. Okay? Because I hated the properties of both statement, but the only place it's true is it's both a loser and a gainer if it's a metalloid. Metals always lose, non-metals always gain. And what are anions going to look like? They're going to look like noble gases. Everybody wants to look like a noble gas. So the big ideas out of there were the driving force. Everybody wants to look like a noble gas. Two ways to get there. Gain electrons or lose electrons. And that's where I want to stop for today. So I'm passing out the instruction sheet for today's lab. There's no back on this one. This is just the instructions. I'll get you the data table stuff, and the other one is just a second. Okay, let's go back on this page. So I'm going to ask you for the next 4 or 5 minutes to read what it has to say about what you're going to do today. We have now finished hour 1 of our 2-hour period. Second page I'm passing out to you should have 2 sides. Just make sure it has both of them.